Hello everyone, my name is Sukumar and today I'll be walking you through my solution to the 8 puzzle problem using 3 different search algorithms: uniform cost search, best first search and A star search. For this assignment, I implemented these algorithms, built a GUI for user interaction and compared their performance using different heuristics. The goal was to analyze how efficiently these algorithms solve the puzzle. So the 8 puzzle problem is a classic sliding tile puzzle where you rearrange the tiles in a 3x3 grid to reach the goal state. So in our problem, the goal state is already given and we have been asked to randomly generate the initial state puzzles and solve them using the different search methods. So there are three search methods are implemented here: uniform cost search, best first search, and A star algorithm. So I'll just explain a overview about these algorithms. So uniform cost search, it basically expands nodes based on path cost only. So it guarantees the optimal solution, but it visits a lot of nodes and can be slow. When it comes to best first search, it expands nodes based only on the heuristic value. It's super fast because it prioritizes the best looking option, but it's not always the shortest path. It might take some bad detours. When it comes to A star, it uses both path cost and heuristic value for a balanced approach, finds the best path faster than UCS. So let's go to the code. So now uh, let's see how I actually implemented this in Java. I structure the code into different classes for better organization. So these are the 5 classes which I have implemented for this. The first class is Puzzle GUI. It handles the graphical interface, user interactions, and tile movement. It features a reset button that generates a new random puzzle state, allowing multiple test runs without restarting the program. And this is the node class. It represents the state of the puzzle and tracks things like parent nodes, path cost, and heuristics. This is the class for uniform cost search. It expands nodes by cost only and guarantees the shortest path, but it's kind of slow since it visits too many nodes. And best first search. It expands nodes based purely on heuristic value, no cost involved here. It's really fast, but often chooses the wrong path because it's a bit greedy. A star search. This is where things get interesting because we have two heuristics to choose from. Manhattan distance, it finds the optimal path. Nilsson sequence score, it expands fewer nodes but sometimes takes a longer path. So for the assignment requirement, it is specifically mentioned as a to use Nilsson sequence. So I implemented both the logic as well and made it easy to switch between the heuristics in the code. We just need to uncomment one line to choose Manhattan or Nilsson. I'll show you during this demo. So, and also I am logging the initial state of the puzzle in the console. Before I run any algorithm, I print the initial state of the puzzle in the console. Why? So for example, if I'm going to run the code, so here we have the initial state as 160375842, and we have an option to swap the tiles. So for example, I can swap it like this. So now our initial state is changed to 316075842. If I'm going to click on any of these buttons, I need to pass the current state as the initial state, right? To make sure the correct state is getting passed, I'm just printing the initial state when we are passing to the search algorithm in the console so that we will get to know, okay, right, the initial state is passed to the algorithm. And to make the puzzle solvable, I included an inversion count check. If the number of inversions is even, the puzzle is solvable. If not, we regenerate it. So this is the logic to check for the inversions. And whenever if the puzzle is not solvable, the code will automatically generate puzzle and it will always give solvable puzzles only. And let's see this in action. I will walk you through how these algorithms perform with different heuristics. So now I am going to run the code. So I have already ran the code. Okay, let's stop it and run it again. So this is our initial state, and we have buttons for reset, UCS, BFS, and A star. So if I click on reset, the puzzle resets to a different random state. So now I'm going to click on UCS. Since it doesn't use any heuristic and it's just going to use the cost alone, if you see, it visits a huge number of nodes but always finds the shortest path. It's 25. Now let's run the same initial state with best first search. So if you see, this one is super fast when compared to UCS, but it's taking a longer path. So if you see, the goal to reach is 47. So in case of a UCS, it just 25 moves to reach the goal, but in case of a BFS, it took 47 moves, which is really a long. And now I'm going to, so now the code is running using Nilsson sequence, and now I am going to run for A star, and A star, if you are seeing, like total moves to reach the goal is 29, but in case of UCS, total moves to reach the goal is 25. So this is one of the difference. We have to note it down here. And so here in the A star search, so this is where I am going to change it to Manhattan. So I'm going to just uncomment this and comment this logic. So now if I run this code, it will be running with Manhattan logic. So now let's see. So now UCS takes 17 steps to reach this goal, and let's see A star. If you see, A star also takes 17 steps. So whenever the Manhattan calculation is used, UCS and A star will always find the optimal solution, and A star's optimal solution will match with the UCS as well. Now I am going to close this code and I'm going to undo my changes. Now I am going to run it with the Nilsson sequence. So UCS takes 26 moves to reach the goal, but A star takes 36 moves to reach the goal. So this is one of the difference. So A star, but however, if you notice, the number of nodes visited in UCS is it's more than a lakh, but in case of A star, it's just 264 nodes, and the runtime is very much lower compared to all the algorithms. So we can clearly see that the number of nodes visited varies based on the puzzle complexity. Some puzzles take way more nodes because of how tiles are arranged. So in case if I want to run the program with the fixed initial state, so if you see here, this is where our code is going to call the method to generate a random solvable puzzle. I have just uncommented that particular step, and I'm going to run using this particular current state. If you see, the current state which I have hard coded is 283.164.705, and the same is coming here in this GUI. And if I click on UCS, it takes just 5 steps to reach the goal, and let's expand it. So how I implemented this solution is, the solution path will be printed in the GUI, and the code will be showing every move, every single move to reach the goal. And in case of a BCS, it's taking 11 moves to the goal, and in case of a star, just 5 moves. But one thing to note down here is, if you see UCS and A star, both are using the same moves, even though we are using the Nilsson sequence. So most of the times Nilsson sequence is optimal, but in case of a when the puzzle complexity varies, sometimes it might be taking a longer path. And here we have the stats from all the 10 runs. So as part of the program assignment, I have done the run for multiple times, like around 10 times, and I have captured the values. And these are the stats, like the best, worst, average values also I have captured it. And based on this, if we see, UCS is great for optimal paths, but is slow since it expands more unnecessary nodes. Best first search is the fastest, but the paths are often much longer. A star is the best balance of efficiency and accuracy, but choosing the right heuristic makes all the difference. Manhattan guarantees optimality, while Nilsson's reduces the number of node expansions but may take a slightly longer path, depends upon the puzzle state. So that's it for my presentation. Thanks for watching. Let me know if you have any questions. Thank you.